The standard deviation is another numerical way of analyzing a data distribution, and it's notorious for being or seeming quite complicated because the formula upon initial inspection seems really horrible and hard to grasp. But it's kind of simple once you break it down. That's what I wanted to do in this video, is look at the building blocks of the standard deviation, talk a little bit about what it is and why we do what we do to calculate it, and we'll actually look at calculating the standard deviation for some of the data sets we've been working on in the previous videos. And I wanted to emphasize the importance of standard deviations. In statistics, it's used a lot to understand how the data works, and we'll be working with it more as the semester progresses. So I'm not saying you should really master it right away, but for today we're going to focus on the math of how it works, and then we'll kind of be using it a lot as the semester goes on. So let's go ahead and look at the book and how it presents the standard deviation, and then let's talk about it and get going on doing some math. So it says the variance S squared of a set of observations is an average of the squares of the deviations of the observation, that's a lot of ofs, from their mean. In symbols, the variance of n observations x1 through xn is blue, and this looks kind of horrible if you have never seen it before, and it's also presented using sigma notation. And then it says the standard deviation S is the square root of the variance S squared. So it's important to denote here, variance is defined to be S squared, or sometimes V, and standard deviation is just the square root of S squared, right? Because the square root of, and notice actually it's the same formula with just a square root around it, which gives us the standard deviation. And we'll talk about why the square root is used with the standard deviation as we talk more about the formula and so forth. But for calculating the standard deviation, it's what I recommend is starting with the variance, and then once you've kind of wrapped your brain around the variance, we can just take the square root to find the standard deviation at the end. And actually, if you've ever had stats before or have any familiarity with standard deviation, the Greek letter sigma, which looks kind of like my hand is backwards, but sort of like a little circle with a little hat on it or something, is used for standard deviation quite commonly as well. I wanted to denote that there's kind of a contextual reason why it's used as S sometimes and sigma in other cases. We'll talk more about that as this semester progresses, but what you want to be careful about is sometimes this formula will be referenced using n instead of n minus 1, and it just sort of depends on the situation you have. We'll cross that bridge when we get to it. For now, just take this as a standard deviation for when you're doing calculations. But basically, let's go ahead and look at the formula. It says that S squared is equal to x1 minus x hat quantity squared plus x2 minus x hat squared plus ... xn minus x hat squared, all divided by n minus 1. And what you'll note right away is the similarity to the average formula, where the mean, or the arithmetic average of numbers, is you add up all the data points and you divide by the number of data. It's like something plus something plus something plus something divided by n. The difference with the variance is we have all these squareds. We have actually the mean built into these parentheses in each case, and we have n minus 1 instead of n. So what is all this and why? Let's kind of break this down. So first of all, notice inside the parentheses we have, instead of just x1 and x2 and x3, we actually have the difference between x1 and x hat, or x bar, whatever you want to call it. X bar, remember that this was the variable we used to describe the mean. So basically what this is saying is, well, what is the difference between the first data point and the mean? And this is what we often refer to as the deviation. So basically each data point has some deviation between the mean. And is a little ways a part of it. And we'll do an example here in a minute, because I think it's hard to understand without this. But basically what this first little parenthesis is going to do is say, well, how far away is our first data point from the average? This one is the second data point, and so forth. Basically, we're looking at all of those deviations. Now, we want to average all the deviations. That's the idea behind the standard deviation. The issue is, if you just add up all of the deviations, since each one is a particular distance from the mean, and the mean is the direct center, if you add up all of the variations, all of the deviations like this, it will actually give you 0 and it won't tell you anything meaningful. So that's one of the reasons we square it is basically, well, some of those are going to be negative, some of them are going to be positive. It's basically removing the negativity between the numbers. It's sort of similar to just taking the absolute value of the variance or of these deviations, which from a more theoretical standpoint, you could use an absolute value instead, but that's just not the way the standard deviation is defined. And again, you might wonder the significance. All of these terms are things we've created to try to understand things. And so it's not a bad idea to ask yourself, well, why is it defined the way it is? Because sometimes things are done a little bit arbitrarily, but in this case, there's sensibility behind it. So essentially, we've got all the deviations, we've squared them to deal with the negativity, and then we're dividing by n-1. It's essentially we're averaging all the deviations, except for, instead of dividing by n data points, we're dividing by n-1 instead. Now, n-1 is kind of a crucial idea for standard deviation, and n-1 is often referred to as the degrees of freedom that we have within our deviations. Let me just go ahead and write that down and fill in the blank on notes. And essentially, kind of referring back to what I was saying before, is if you add up all of the deviations, essentially, they're always going to add up to 0 if you add up all deviations together. Which is kind of a way of saying, well, nothing really happens if you do that. So if you remove one data point, actually, basically, since the sum of all of them must be 0, let's say you know 9 out of 10 data points and one of them is missing. You can always find that 10th data point because you know, if you know 9 out of the 10 variations, the last one is not unknown. And essentially we'd say that there's only 9 degrees of freedom in that context because the last one always must be known. So essentially, if we had 10 data points, only 9 of those are actually going to have freedom, have variation, and that's why we want to average it based on one less than the number of observations, because the last one we say is not free. It's always going to be fixed in that sort of way. And again, this is all a little bit strange. It's very abstract, so bear with me. But if that makes some basic sense, basically, all of them are free except for the last one. And actually, when it comes to complete populations, if you know all of the data, technically you would shift this formula to use n instead. At the end of the day, I would just say don't really worry about it. Often we refer to such a standard deviation as the standard deviation of a data sample, in which context you do use n-1, not n. And we'll circle back to other cases when you would use n instead later. But what you do need to be careful about is if you go into and use a standard deviation calculator, there are different ways a standard deviation is defined based on different contexts. So if you're getting different answers than you think you should be, it might be because you're using the wrong type of standard deviation. There are different types. Again, we'll worry about that later. For now, take this as law. Let's actually get into doing some calculations because I don't want this video to get too long. So let's go ahead and calculate the variance in standard deviation for Amanda's quiz scores and talk about what that means. So if we recall an example from a few videos ago, Amanda took 7 quizzes and she had these scores. We found the mean, median, etc. Actually, I think that's just right over here. We can go back and reference what she had. Her mean quiz score was, she had an 87 average. Her median score was 91. And so on. So let's go ahead and calculate the standard deviation and the variance, and then we'll try to figure out what is this telling us, because it is not a simple calculation. So what I recommend doing for calculating a standard deviation is first figuring out what are all of the normal deviations. Essentially, how far apart is each data point from the mean? So we could start off with, well, we need to know what is x1 minus x bar, what is x2 minus x bar, what is x3 minus x bar? Because that's essentially what is built into each parentheses. And remember, all this means is, well, x1 means the first data point. X bar is the mean. And we already had the mean calculated from before, so let's just go ahead and write that down as a reference. her average test score was 87. And so if we're going to look at, and I'll go ahead and organize this into like a table, because I think this is the easiest way to sort of organize all the calculations that go into the standard deviation. And this is just how I like to do it. Other people do it a little differently. Doesn't really matter how you do it as long as you can do all this. But the way I like to do it is very intuitive. So first I want to figure out, well, how far away is each data point from the mean? Well, 100 minus 87 is 13. So her first quiz, she was 13 above her average. Her second quiz, she was 5 above her average. Her third quiz, that was the one she really bombed, 54. And again, I would want to make sure to put that one first. This would actually be a negative deviation. So 54 minus 87 would be negative 33. Technically, the sign won't end up mattering because we're going to square them anyways, as I was saying before. And then I'll go ahead and write this column. This is the deviations column. And then what I'll then do next is square them all. Because that's what I need to do, right? I need to calculate each of those deviations for every single data point, add them all up and square them. So X4 was 91. That one was above her average by 4. X5 was 83. That was underneath her average by 4. X6 was 99. That was above her average by 12. And then X7 was 90. That was over her average by 3. So basically, those would be all of her deviations. And yeah, you can go ahead and add those up, see what you get. But as I said before, that should be 0. Again, assuming your mean is correct. Let's go ahead and do that just for now that I'm looking at it. I want to make sure. 18, 22, 34, 36 would be the sum of all the deviations. For some reason, I'm getting 37 when I look at all of the negatives. So maybe I goofed up. Whatever, let's just move on. So now if we're squaring those deviations, because what I need to do is find the sum of all of the square of the deviations here. 13 squared is 169. 5 squared is 25. I do not know 33 squared off the top of my head, but 33 squared is 1089. 4 squared is 16. 12 squared, 144, and 3 squared is 9. And remember, squaring will always become positive because you're multiplying the number by itself. Okay, now basically, in order to calculate the variance, it's the sum of all of the deviations squared divided by n minus 1. So what I want to do is figure out, well, what's the sum, like what's the total of all of those squared deviations. So let's go ahead and add all that up. 169. And it's important to note the standard deviation is not an easy thing to calculate. Even with just 7 scores, it's quite tedious. But you can often put use to calculators or other things to help you. And we'll work on using other resources to calculate a standard deviation. But I think it's important to really explore how you actually do it from scratch, because it helps us understand what it means. Okay, sorry, trying to add all these up. Adding up all those deviations, we've got 1468. So I'm going to go ahead and note that right here. And that would be, so kind of writing down, well, what's the variance? The variance is the sum of all of the square deviations, which is 1468. Oops, let me rewrite that. That came out a little messy. 1468, and that would be divided by the number of objects. Well, not the number of objects like with mean, it's n minus 1. So instead of, she had 7 quiz scores, so I'm going to divide it by 6 instead. Because again, one of those quiz scores is said to be not free, because our degrees of freedom is 1 less than the number of observations. And so when you're trying to memorize all this, those are the 2 key things I would remember. Figure out how they really find the mean. I guess there's more than 2 things. Find the mean, find how much each data point varies from the mean, square those, add them all up, and divide by the number of things minus 1. All that being said, that will give us our variance. So divide that by 6. Here our variance should be, it looks like 244.6 repeating, or 244 and 2/3. And so last step is to actually find the standard deviation. It's very easy to forget after doing all this math. Whoops, what am I doing? After doing all this math, really easy to forget, okay, I actually need to take the square root of all that crap to find the actual standard deviation. So the standard deviation is just the square root of the variance, because the variance is defined to be s squared. So s is, of course, the square root based on algebra, right? Because the square root of something squared is itself. So s is equal to the square root of s squared based on algebraic cancellation, or the square root of that thing I just found out. So really, after doing those other 5 steps, 6th step, take the square root. That would give you your standard deviation. And if you want to do this in the TI-84, you could just type square root of answer, because notice that the answer is, you can't see it as the calculator is now, but if you look, the answer key is right above the negative symbol in your calculator. And if you want to access it, you just hit second negative, and that will take whatever your previous answer was, and you can then operate upon that and take the square root of an answer like that. And basically all that's going to do is take the square root of what I had right there, which is 15.564. And another thing I'd like to mention is that just for notation, if you're ever going to round, like rounding is something that's totally fine to do in a lot of contexts. Though for finding the standard deviation, you don't want to round your variance before you plug it in if you're doing calculations step by step by step. Because let's say you rounded this to 245. If you then take the square root of 245, that's going to have a little bit of rounding error. And notice your standard deviation might have a little bit of error to it too. And if you're working on the online homework and trying to figure out the answer, it might tell you you're wrong just because of something simple like something rounding. So my point is, don't round until the very end. And if you need a round, use as many decimals as you can so that that rounding error does not compound as you're doing calculations upon it. But in this case, yeah, let's just go ahead and round it to the nearest hundredth. So 15.64 would be our standard deviation, rounded. But since it is a square root of a number that's not a perfect square, this is going to be irrational. Technically, it's a very complex number in its exact form, but an approximation suffices. And we come up with our standard deviation for Amanda's test scores. And before I wrap up this video, what does that mean? That's a whole nother question, a whole nother can of worms to open up. But basically, we're gonna get more into how the standard deviation can help us understand it. But it gives us a sense for how messed up the data is. A smaller standard deviation means the data is very close together. It's clumped. There's no variation. And the larger the standard deviation means the data is further spread apart. There's more weirdness. There's more outliers. There's more unusual stuff happening. It's kind of like, is everything the same? Standard deviation small. Everything different? Standard deviation large. And I put sort of some bullet points here to kind of help you with this too. But, and like if we walk back through the math, we can kind of see why this works here. Because basically the numerator here was a measure of how different the numbers were, right? The deviation as it is defined tells you how far away from the average is it. Certain points like her 54 was very far away from the mean, and her 100 was technically fairly far from her average as well. Those data points you'd say have higher variance. And the points that were very close have lower variance. And so basically this is like a way of measuring how much variance does this have. So you might wonder, well, why do we square it? Well, again, really the main reason is because it's negative and we want to sort of normalize them all. And notice we ended up taking the square root anyways. That's another reason to sort of help yourself remember, why do I need to take the square root here? Is because, well, we squared it in the first place. We took those numbers and squared them. So we kind of want to undo that to sort of normalize them now to the normal context of these are exam scores. And this answer is technically, it's kind of like an exam score. 15 to 16 points is the standard deviation. And later in the semester, we're going to talk about how most data falls within 1 or 2 or 3 standard deviations from the mean. And what you can see in this case is that, like, it's sort of like the quartiles in a sort of a sense where most of your data will fall within 1 standard deviation, but outliers might fall between 2 and 3 standard deviations away from the mean. And since the mean was 87, actually, in this case, every single one of her quizzes was within 15 points of 87, except for her 54. The 54 was quite a bit further away, and standard deviation kind of gives you the measurement of how far away does it need to be in sort of a similar way. Also, standard deviation cannot be negative because it's a sum of purely positive numbers, but it could hypothetically be 0. If all of your deviations end up being 0, then all of these would be 0 and your standard deviation would end up being 0. But that would only be in the case when all the data was literally homogeneous. If there was no difference between it at all. So if, like, let's say we were measuring our students' age, they were all 19 years old. The standard deviation would be 0 because they're all the same. So 0 is kind of a picture of everything is the same. Everybody's exactly the same. Very unusual. Your standard deviation for a real data set probably won't be 0. But if it's very close to 0, that means there's very little variability. And when it gets higher and higher and higher, it just means that things are further and further and further apart. And the standard deviation is susceptible to outliers. Like we had one data point which kind of was making up the most of the size of the standard deviation, right? Was that the outlier, which was her score of 54. If you exclude that 54, her standard deviation is going to be a lot lower, and it's just going to be a lot more homogeneous, right? Because she had that one bad quiz. It's going to basically, your standard deviation will shoot way up. And I'd say, if it's like 5 or 10 or 15, that's starting to indicate that things are further and further away. And the standard deviation, it's not an overarching scale because it depends on the size of the numbers as well. That will wrap up this sort of video series. Sorry, this video got kind of long. In the last video, I wanted to show you how you can do a lot of this math using Excel. In our labs, we're going to be using Excel and or R to help us do a lot of these same sort of calculations throughout the semester. And as you can see, sometimes things are pretty tedious to do by hand. And so with a computer or a calculator, these things can be done easily. And I want to show you how to do that next.